Tonight, we're going to explore something that has no comparison anywhere in the known universe. An object so extreme that physicists had to invent new language to describe it. A black hole so massive that if you placed it where our sun sits, its event horizon the point of no return, the boundary where nothing escapes would extend past Jupiter, past Saturn, past Uranus, past Neptune, all the way out to the edge of our solar system and beyond. It is called TON 618. It is a quasar located 10.4 billion light-years from Earth. And at its center sits the most massive black hole ever confirmed by science. A black hole containing 66 billion times the mass of our Sun. 66 billion solar masses. The Milky Way's central black hole, Sagittarius A star, contains 4 million solar masses. That already sounds impossible. TON 618 is 16,500 times more massive than that. The entire Milky Way galaxy contains roughly 200 billion stars. The black hole at the center of TON 618 contains the mass equivalent of 330 Milky Ways worth of stars. Collapsed, compressed, gone. By the end of tonight, you're going to understand what a black hole actually is and how one forms. You're going to understand the scale of TON 618 in terms that will change how you think about the universe. You're going to understand the discovery story, how we found it, how we measured it, and why astronomers were stunned by the number. You're going to understand what an ultramassive black hole does to space-time around it, and what it means that an object this extreme exists at all. And you're going to understand what TON 618 tells us about the universe's most violent and productive epoch, a time billions of years ago. When the cosmos was building things on a scale it will never build again. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand TON 618, you need to start with a number, not a complex equation. Just a number, one that, if you sit with it long enough, begins to do something unusual to the way you think about size and scale and your own position in the cosmos. The number is 66 billion. 66 billion solar masses. That is the mass of the black hole at the center of TON 618. Now, a solar mass is roughly 2 times 10 to the power of 30 kilograms. That is 2 followed by 30 zeros in kilograms. Multiply that by 66 billion, and you have the mass of TON 618. The number is so large it loses meaning almost immediately. That's the problem with describing the most extreme objects in the universe. The numbers stop corresponding to anything the human mind can visualize. So tonight, we're going to build the scale, step by step. We're going to start from something you can picture, a black hole the size of a city, and work our way outward until we arrive at TON 618, and you understand in your bones what 66 billion solar masses actually means. But before we get to the scale, we need to understand what a black hole is. Because black hole is one of the most commonly misunderstood phrases in science. Most people have a picture of it. Most of that picture is wrong. Let's fix that. In the 1950s and 1960s, radio telescopes began detecting powerful sources of radio waves from deep space. When optical telescopes looked at the same positions, they found what appeared to be stars. But they weren't stars. They were far too distant and far too bright for anything stellar. They looked like stars, but they had the luminosities of entire galaxies. Sometimes, many hundreds of times the luminosity of entire galaxies. Astronomers called them quasi-stellar radio sources, quasars. Later, the name was broadened to include similar objects detected in optical wavelengths rather than radio. The general term is now quasi-stellar object, or QSO. Quasar is still commonly used. For years, no one was sure what they were. Their spectra were strange. The emission lines were shifted so dramatically toward the red end of the spectrum that early astronomers didn't recognize them as normal atomic emission lines at all. When astronomers finally understood the redshifts, the distances became clear. These objects were billions of light-years away, and yet they were bright enough to see from Earth. Bright enough in some cases to be visible with a modest telescope, despite being across most of the observable universe. The energy output required to explain this was staggering. There was no known physical process that could explain it. A quasar producing the light output of hundreds of galaxies, from a region only about the size of our solar system, seemed to violate the laws of physics, as understood at the time. The solution took decades to fully establish, but it is now understood clearly. A quasar is what happens when a supermassive black hole is actively feeding. When gas, dust, or disrupted stars fall toward a supermassive black hole, they don't fall straight in. They have angular momentum they orbit, and they form a flat, rotating structure called an accretion disk. The accretion disk is incredibly hot. Material spiraling inward through the disk moves faster and faster as it gets closer to the black hole. Friction between adjacent orbiting material heats the gas to millions of degrees. At those temperatures, it radiates intensely across the electromagnetic spectrum. Visible light, ultraviolet, X-rays. The energy release in this process is extraordinarily efficient. Nuclear fusion, which powers stars, converts about 0.7% of mass to energy. Accretion onto a spinning black hole can convert 10 to 40% of infalling mass to energy. It is among the most efficient energy-generating processes in the universe. When enough material is falling in, the accretion disk can outshine the entire host galaxy. The black hole is a tiny region of space, a point, essentially, but the accretion disk around it becomes the most luminous object for billions of light-years in every direction. That is a quasar. Quasars are also associated with relativistic jets, narrow beams of plasma and magnetic field ejected along the black hole's rotation axis at close to the speed of light. These jets can extend for millions of light-years, pumping enormous energy into the surrounding intergalactic medium. They can suppress star formation across entire galaxy clusters. They are among the most violent and far-reaching phenomena in the universe. Here is the crucial detail. Quasars are not evenly distributed through cosmic time. They peaked in abundance roughly 10 to 12 billion years ago. That corresponds to redshifts of Z equals 2 to 3, the period when the universe was between 2 and 3 billion years old. At that epoch, the universe was denser, gas was more plentiful, galaxies were colliding more frequently, and supermassive black holes had abundant fuel to feed on. Today, most supermassive black holes are starving. The universe has expanded. Galaxies have spread apart. Gas has been consumed or expelled. The great age of quasars is over. When we see quasars today, we are looking at them across enormous cosmic distances, seeing them as they were billions of years ago, during that violent epoch. Ton 618 is a quasar. We see it as it was 10.4 billion years ago, when the universe was only 3.4 billion years old. At that moment in cosmic history, Ton 618 was one of the most energetic objects in existence. Its accretion disk was pouring out light equivalent to 140 trillion suns. 140 trillion suns from a single object. And at the center of that accretion disk, hidden inside its own event horizon, was a black hole containing 66 billion solar masses. How do we know that? How do we measure the mass of something we cannot see across 10 billion light-years of space? Ton 618 was first catalogued in 1957 as part of the Tunnan-Cintla Catalogue, a survey of blue objects in the sky conducted at the Tunnan-Cintla Observatory in Mexico. The name Ton 618 simply refers to its position in that catalogue. Entry 618. At that point, it was just a faint blue smudge, nothing obviously remarkable among thousands of similar objects. It was re-examined in later surveys and identified as a quasar in the 1970s, when radio surveys began matching positions with optical objects and measuring the characteristic redshifted spectra. Its redshift of Z equals 2.219 placed it at a distance of roughly 10.4 billion light-years. That made it a quasar from the peak epoch of quasar activity, 10.4 billion years ago. It had been known as an unusually luminous quasar for decades, but measuring the mass of its central black hole required a technique that wasn't fully developed and applied to Ton 618 until more recently. The technique is called reverberation mapping. Here is how it works. Around an active quasar's central black hole and accretion disk, there are clouds of gas. These clouds are illuminated by the radiation from the accretion disk. When the brightness of the accretion disk fluctuates, and quasar accretion disks fluctuate constantly, those gas clouds respond. They brighten and dim in response to the accretion disk, but with a delay. The delay is the light travel time from the disk to the cloud. By measuring this delay, you can calculate the distance from the accretion disk to the broad emission line region, the zone where the gas clouds are located. That gives you a physical size. Now here is where Newton and Kepler step in. The gas clouds are orbiting the black hole. Their orbital velocities can be measured from the width of their spectral emission lines. Faster moving gas produces broader emission lines. If you know the orbital velocity of material and the orbital radius, you can calculate the central mass using the same orbital mechanics used to weigh planets and stars. Velocity squared times radius divided by the gravitational constant gives you the mass. The measurement for Ton 618 was published in a detailed study and gave a result of 66 billion solar masses, with an uncertainty of a few billion solar masses in either direction. The black hole mass is confirmed by multiple independent analyses. 66 billion solar masses. To understand what this means, you need to understand what the Schwarzschild radius of this object is. The Schwarzschild radius is the radius of the event horizon for a non-rotating black hole. It scales linearly with mass. For every solar mass, the Schwarzschild radius grows by about 3 kilometers. For Ton 618 66 billion solar masses, the Schwarzschild radius is approximately 196 billion kilometers. The distance from Earth to the Sun is 150 million kilometers. Ton 618's event horizon is 1,307 times the Earth-Sun distance. The average distance from the Sun to Pluto, the outer edge of our solar system, by conventional measure, is about 5.9 billion kilometers. Ton 618's event horizon is approximately 33 times the diameter of Pluto's orbit. If you placed Ton 618 where our Sun sits, its event horizon would reach to roughly 4 times Pluto's distance. Our entire solar system, every planet, every moon, the Kuiper belt, most of the outer solar system would sit inside the event horizon of Ton 618. Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and everything between them. All inside, all gone. Beyond the point of no return, the Sun's corona, its outermost atmospheric layer, extends about 1 to 3 solar radii. Ton 618's event horizon is 33 times the diameter of Pluto's orbit. These are not numbers on the same scale. They are not comparable. They represent fundamentally different classes of object, differing in mass by a factor of 16.5 million. And Ton 618 is not just a big black hole. It is the biggest black hole we have ever confirmed. As of our current observations, it holds the record 66 billion solar masses. Nothing confirmed comes close. But understanding the number is only the beginning. Understanding what it means, what happens in the space around an object this massive, what gravity does at these scales, what Ton 618 looked like when it was active, that is where the story becomes genuinely strange. Let's build the scale properly, starting small, working our way up until we reach Ton 618. The first black holes ever discovered were stellar mass black holes. The smallest confirmed black hole is a few solar masses. Let's use 5 solar masses as a representative small stellar black hole. Its Schwarzschild radius, the radius of its event horizon, is about 15 kilometers. If you drew a circle with a radius of 15 kilometers, that's roughly the city of Paris from north to south. Everything inside that circle, gone. That is a 5 solar mass black hole. Small. The event horizon of a black hole formed from the core of a dead star, smaller than the width of a mid-sized city. Now scale up. A typical stellar mass black hole formed in a supernova is 20 to 30 solar masses. Its event horizon is 60 to 90 kilometers across, about the distance from the center of London to the edge of Greater London, or the full width of a small American city. Not the whole city. Just across it, the most massive stellar black holes formed from the largest stars reach perhaps 100 solar masses, in rare cases. Event horizon diameter, about 600 kilometers. That's roughly the distance from New York to Boston, or London to Edinburgh, or Paris to Lyon. Still something a human can picture. Still something with a geographic analog. Now jump to the intermediate range. An intermediate mass black hole of 10,000 solar masses has an event horizon with a diameter of about 60,000 kilometers. That is roughly the diameter of Saturn. A black hole with an event horizon the size of a gas giant. Still imaginable. At 1 million solar masses now entering true supermassive territory, the event horizon diameter is 6 million kilometers. The Sun's diameter is 1.4 million kilometers. A million solar mass black hole has an event horizon about 4 times the diameter of the Sun. You can picture the Sun. This is 4 of those. Still within the range of things you can hold in your mind. Sagittarius A star, our own Milky Way's central black hole. 4 million solar masses. Event horizon diameter about 24 million kilometers. The Sun is 150 million kilometers from Earth. Sagittarius A star's event horizon is about 1/6 the distance from Earth to the Sun. If Sagittarius A star were where the Sun is, its event horizon would extend about 12 million kilometers in every direction past Mercury's orbit, but not far enough to reach Venus. The inner solar system would still exist. Earth, at 150 million kilometers, would be fine. Terrified, but fine. Now the giant elliptical galaxies. M87 star, the black hole at the center of galaxy Messier 87, was the first black hole ever photographed, the famous orange ring image from the Event Horizon Telescope in 2019. 6.5 billion solar masses. Event horizon diameter, about 38 billion kilometers. The Earth to Pluto distance is about 5.9 billion kilometers. M87 star's event horizon is more than 6 times that distance. If M87 star were in our solar system, the event horizon would extend well beyond Pluto. The entire planetary solar system would be inside. That is 6.5 billion solar masses. That was the most massive confirmed black hole for many years. It held the record. Ton 618 broke it. Ton 618, 66 billion solar masses. 10 times more massive than M87 star. Event horizon diameter, approximately 392 billion kilometers. Earth to Pluto, 5.9 billion kilometers. Ton 618's event horizon spans this distance 66 times over. The entire solar system, all 8 planets, the asteroid belt, the Kuiper belt, all the space between, sits many times over inside the event horizon of Ton 618. Another way to picture it, the nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. 1 light-year is approximately 9.46 trillion kilometers. Proxima Centauri is roughly 40 trillion kilometers from the Sun. Ton 618's event horizon radius is about 196 billion kilometers, about 1/200th of the distance to Proxima Centauri. So from where our Sun sits, the event horizon of a Ton 618-sized black hole at the Sun's location would extend roughly 1% of the way to the nearest star. Not to the nearest star, not even close. But remember, that is the event horizon of a single object, a point, cosmologically speaking, a thing sitting at the center of a galaxy. And it is vast enough to swallow our entire solar system, with room to spare. There is one more comparison that puts this in the starkest possible terms. The Milky Way galaxy contains roughly 200 billion stars. Our Sun is an average star. If you could take all 200 billion stars of the Milky Way and compress them into a single point, you would have a black hole of about 200 billion solar masses. Ton 618 contains 66 billion solar masses. It is roughly 1/3 the total stellar mass of an entire Milky Way-sized galaxy. Collapsed. Gone. This is what 66 billion solar masses means. It means the equivalent of compressing 1/3 of all the stars in a galaxy like ours into a single object hidden behind an event horizon the size of a solar system. It means an object where gravity is so extreme that space-time itself has lost the concept of outward direction for a region of space larger than the distance between the planets. And this object exists. It is real. It has been measured. It sits 10.4 billion light-years from Earth, at the center of a quasar that, at its peak, was pouring out 140 trillion solar luminosities. Let's talk about what that environment looks like. what Ton 618 actually is as a physical system. Ton 618 is classified as a broad absorption line quasar, or BAL quasar. This means the spectrum of its light shows broad absorption features caused by fast-moving gas being blown away from the central engine at velocities of up to 10% the speed of light. The gas is being driven outward by the intense radiation pressure of the quasar's accretion disk. These outflows are called quasar winds, and they play an enormous role in the evolution of the host galaxy. The accretion disk itself is a structure unlike anything in our solar system or our galaxy. The material falling toward the black hole forms a flat, rotating disk typically extending from just outside the innermost stable circular orbit, the closest stable orbit around the black hole, out to distances of perhaps a light year or more. The disk is not uniform. It has temperature gradients that decrease with distance from the center. The innermost regions, just outside the event horizon, reach temperatures of millions of degrees, radiating X-rays. The cooler outer regions glow in ultraviolet and optical light. The combined emission from the full disk produces the characteristic blue-white color of quasars. For Ton 618, the accretion disk luminosity is approximately 4 times 10 to the 40 watts. To put that in perspective, the Sun's luminosity is about 3.8 times 10 to the 26 watts. Ton 618 outshines the Sun by a factor of roughly 100 trillion times the luminosity of the Sun. From a single object, the Milky Way galaxy, with its 200 billion stars, has a total luminosity of about 5 times 10 to the 36 watts. Ton 618 outshines the entire Milky Way by a factor of about 10,000. At the innermost stable circular orbit around a black hole, the orbital velocity for a non-rotating black hole is a significant fraction of the speed of light. For a rotating black hole, and Ton 618, like essentially all black holes of any significant size, is almost certainly rotating the innermost stable orbit, can be much closer, and orbital velocities approach the speed of light more closely. Material at the inner edge of the accretion disk is moving at a substantial fraction of 300,000 kilometers per second. The friction between adjacent orbiting material at this velocity generates the heat that drives the luminosity. Now consider the photon sphere. For any black hole, there is a region outside the event horizon where light itself orbits. Not escaping, not falling in, but orbiting. For a non-rotating black hole, this is at 1.5 times the Schwarzschild radius. For Ton 618, that puts the photon sphere at a radius of about 294 billion kilometers. Photons circling Ton 618 in the photon sphere take months to complete a single orbit. The region around Ton 618 is also blasting out relativistic jets. Quasar jets are collimated streams of plasma and magnetic field launched along the black hole's spin axis by processes related to the interaction of the rotating black hole with the surrounding magnetic field. The Blandford-Znajek mechanism, which extracts rotational energy from the spinning black hole itself, is believed to be the primary driver. The jet material is accelerated to 99% or more of the speed of light and can extend for millions of light years from the central engine. These jets don't just travel through space. They do things to space. They push against the intergalactic medium, creating enormous cavities bubbles of hot plasma millions of light years across. They heat the gas in galaxy clusters, preventing it from cooling and forming new stars. A single quasar like Ton 618, through its jets, can regulate star formation across a volume of space many millions of light-years in extent. The most powerful quasars in the universe are not just bright objects. They are geological forces on cosmic scales, reshaping the environments of entire galaxy clusters. The host galaxy of TON 618, the galaxy that contains this black hole, at its center, is not well resolved at its distance of 10.4 billion light-years. What we can infer is that it was almost certainly a large, gas-rich system. To feed a black hole to 66 billion solar masses in only a few billion years of cosmic time, enormous amounts of gas had to be funneled to the galactic center. This typically requires a gas-rich galaxy, possibly in the process of merging with another galaxy, as galaxy mergers are one of the primary mechanisms for driving gas to galactic centers and triggering quasar activity. At its peak activity, the region within a few light-years of the central black hole in TON 618 was among the most extreme environments in the known universe. A 66 billion solar mass black hole, an accretion disk brighter than 10,000 Milky Ways, a photon sphere where light itself was trapped in orbit, relativistic jets screaming outward at nearly the speed of light, gas clouds moving at thousands of kilometers per second, X-ray emissions so intense it would be lethal billions of miles away. And surrounding all of this, the normal machinery of galaxy formation gas clouds, star formation regions, young stellar clusters being battered and heated and blown apart by the radiation and jets of the central engine. This is what TON 618 was, 10.4 billion years ago. Today it is dark. The fuel ran out. The quasar era ended. TON 618 almost certainly still exists, now a dormant giant at the center of an evolved galaxy. Its black hole still there, still enormous, but no longer fed, no longer burning, waiting. The existence of TON 618 poses a fundamental question that cosmologists have been wrestling with for decades. How does a black hole become 66 billion solar masses? This is not a trivial question. It is, in fact, one of the most challenging problems in observational cosmology. Let's think about the timeline. The universe is 13.8 billion years old. TON 618 is at a redshift of Z equals 2.219, which means we see it as it was 10.4 billion years ago. The universe was 3.4 billion years old when the light we detect from TON 618 left its source. That gives us 3.4 billion years from the Big Bang for the black hole at the center of TON 618 to reach 66 billion solar masses. How fast can a black hole grow? The maximum accretion rate for a black hole is set by the Eddington limit. This is the point at which the outward radiation pressure from the accretion disk balances the inward gravitational pull, preventing more material from falling in. At the Eddington limit, a black hole doubles its mass in a characteristic timescale of roughly 45 million years, called the Salpeter time. If you start with a black hole seed and let it grow at the Eddington rate continuously, you can calculate how large it can get in a given time. Starting from a stellar mass black hole of perhaps 100 solar masses at, say, 500 million years after the Big Bang, and growing at the Eddington rate continuously until 3.4 billion years after the Big Bang, that is, 2.9 billion years of growth time, the maximum mass you could reach is approximately 10 to the 22 solar masses. Far more than enough. So in principle, growing to 66 billion solar masses in 3.4 billion years is possible. The Eddington limit allows it. The problem is that black holes in reality do not accrete continuously at the Eddington rate. Observations of quasars suggest that most supermassive black holes spend only a small fraction of their time actively accreting at high rates. The duty cycle, the fraction of time spent in active quasar mode, is estimated at a few percent for most supermassive black holes. Most of the time, they are dormant. If Ton 618's black hole had a typical duty cycle of a few percent, it would not have had enough time to reach 66 billion solar masses by 3.4 billion years after the Big Bang. This means one or more of the following must be true. First, Ton 618's black hole had an unusually high accretion efficiency, spending an above-average fraction of its time in active quasar mode. Second, it was fed by an extraordinarily abundant gas supply, perhaps due to multiple galaxy mergers delivering fresh material repeatedly. Third, it started from an unusually massive seed black hole, bypassing the slow early growth phase. Fourth, at certain periods, it accreted above the Eddington rate, what is called super-Eddington accretion, which recent observations suggest is possible for brief periods under the right conditions. The seed black hole question is particularly interesting. Where did the black hole at the center of Ton 618 start? In standard models, the seeds of supermassive black holes are either stellar remnants, the black holes left behind by the first generation of massive stars, the population 3 stars, or direct collapse black holes, formed when enormous gas clouds in the early universe collapsed directly into black holes without ever forming stars. Population 3 stellar remnants were likely 100 to 1,000 solar masses. To grow from 1,000 solar masses to 66 billion solar masses in 3.4 billion years requires sustained accretion that is difficult to achieve under realistic conditions. The small starting mass is the bottleneck. Direct collapse black holes would have started much larger, perhaps 100,000 to 1 million solar masses. Starting from 1 million solar masses makes the growth problem much more tractable. You need far fewer doublings to reach 66 billion. The leading theoretical picture for objects like Ton 618 involves a combination of a massive seed black hole formed by direct collapse in the early universe, sustained by an unusually abundant and well-funneled gas supply, possibly driven by multiple galaxy mergers, and exhibiting periods of rapid super-Eddington growth during its most active phases. What the James Webb Space Telescope is now finding complicates this further. As we discussed in the context of the early universe discoveries, JWST is detecting supermassive black holes at even higher redshifts Z, greater than 10, meaning the universe was less than 500 million years old, that are already surprisingly massive. These early, massive black holes suggest that the seeds formed very quickly after the Big Bang and grew very fast in the universe's first few hundred million years. The existence of Ton 618 is consistent with this picture. It is the extreme end of a distribution of objects that all suggest the early universe was more efficient at building massive structures, both galaxies and black holes, than any model had predicted. There is something profound about this. The universe's first billion years were, apparently, its most productive. Not in terms of total mass processed, but in terms of efficiency, in terms of the rate at which enormous structures were assembled. The cosmos front-loaded its most dramatic construction. Ton 618 is one of the monuments left over from that era. Let's do a thought experiment. Imagine approaching Ton 618, not from 10.4 billion light-years away, up close, flying toward it in a spacecraft that somehow survives the radiation, The jets, the accretion disk, everything and approaching the event horizon itself. What would you experience? Far away, the gravitational effects would be invisible. Space would look normal. Stars would appear undistorted. Ton 618's black hole. With no glowing accretion disk today, remember, it is now a dormant black hole, would be invisible. You would not know it was there except by watching your trajectory bend. As you approached, the first notable effect would be gravitational lensing. The black hole's gravity bends light. Stars behind the black hole would appear displaced. Stars near the edge of the black hole would be smeared into arcs. If you were precisely aligned with the background star, you would see a complete ring of light around the black hole, an Einstein ring. The universe behind you would appear distorted, compressed. Strange. As you fell closer, time dilation would become noticeable. Gravity slows time. The stronger the gravitational field, the slower time runs. Clocks in a stronger gravitational field run slower than clocks in a weaker one. This is not a theoretical prediction only. It is a measured fact, demonstrated by GPS satellites, which must have their clocks corrected for both special relativistic time dilation due to velocity and general relativistic time dilation due to the weaker gravitational field at orbital altitude. Taken together, GPS clocks run about 38 microseconds per day faster than they would on Earth's surface, and the GPS system must account for this to function. Near Ton 618's event horizon, time dilation would be extreme. For an observer falling toward the event horizon, subjective time passes normally. You would not feel time slowing, but for an observer watching you from far away, you would appear to slow down as you approach the event horizon, your image increasingly red-shifted and frozen in time. An outside observer would never actually see you cross the event horizon. From their perspective, you would appear to freeze at the boundary, fade as your light became infinitely red-shifted, and eventually become invisible. You would never appear to cross. From your perspective, you would cross the event horizon and not immediately notice. There is no local marker at the event horizon for a large black hole. No wall, no flash of light, no sensation of transition. You simply continue falling. Here is something counterintuitive. For a small black hole, a stellar mass black hole of 10 solar masses, with an event horizon 30 kilometers across, tidal forces at the event horizon are extreme. The difference in gravitational pull between your head and your feet is enormous. You would be spaghettified, stretched vertically and compressed horizontally long before you reached the event horizon. For Ton 618, the opposite is true. Because the event horizon is so large, 196 billion kilometers in radius, the tidal forces at the event horizon are surprisingly weak. The gradient of gravity across a human-sized object at Ton 618's event horizon is gentle. You would cross the event horizon without feeling any particular tidal stress. The gravitational field is intense in absolute terms you could not escape, but the rate of change across a small distance is modest. You would cross the event horizon of Ton 618 and feel nothing unusual. You would continue to see light. Stars would still be visible, though increasingly distorted. You would be inside the event horizon and you would not know it. Unless you looked at your instruments. Your instruments would show that every trajectory available to you leads inward. There is no direction that leads out. You are inside the region where all futures lead to the singularity. You have, without any sensation of transition, entered a region of space-time from which there is no return. Eventually for ton 618, eventually could be hours or even days of subjective time. Given the enormous scale, tidal forces would become significant as you approached the true center. Then spaghettification. Then the singularity. Then our physics breaks down and we don't know what happens. The crossing of ton 618's event horizon is perhaps the most cinematic possible version of falling into a black hole. Vast, slow, invisible in the moment. The most profound transition in the physics of space-time, felt as nothing at all, until it is too late. But there is one more aspect of ton 618's scale that we have not yet discussed, something that comes directly from its mass and that has no analog in our everyday experience of physics. The gravitational redshift at the photon sphere. A photon escaping from just outside the event horizon of a black hole must do work against gravity. In doing so, it loses energy. Losing energy means losing frequency. Lower frequency means longer wavelength. The light is shifted toward the red end of the spectrum. For light trying to escape from very close to the event horizon, this redshift is enormous. Light emitted just outside the event horizon arrives at infinity, infinitely redshifted, all its energy extracted by the gravitational climb. This is the physical basis for the black hole being black. Light cannot escape, because any attempt to escape costs more energy than the photon has. For ton 618, a photon emitted from the innermost stable orbit around the black hole would arrive at a distant observer, shifted in wavelength by a factor of several. X-rays emitted near the black hole might arrive as visible or even infrared light. The universe, seen from within a few event horizon radii of ton 618, looks strange, redshifted, distorted. The sky would appear bright and compressed in the direction you came from, dark and empty in the direction of the black hole. A gravitational lens of incomprehensible size. This is the physics of the event horizon. And it is the physics that will apply somewhere in the universe right now, not 10.4 billion years ago, but now, at this moment, to the dormant remnant of ton 618, still sitting at the center of its host galaxy, dark and silent, waiting. Ton 618 is not unique. It is extreme, but it is not alone. It represents one end of a distribution of objects that populate the most violent era in the universe's history. The epoch from roughly 1 billion to 4 billion years after the Big Bang is sometimes called the quasar epoch, or the cosmic noon. It is the period of peak quasar activity, peak star formation, peak galaxy merger rates, and peak rate of black hole growth. During this epoch, the universe was smaller, denser, and more active than at any other time in its history, before or since. The cosmic microwave background gives us the universe at 380,000 years old, uniform, smooth, nearly featureless. By 1 billion years after the Big Bang, the universe had already built structures. Dark matter halos had formed. Gas had cooled into the first galaxies. The first quasars were igniting. Between 1 and 4 billion years, galaxy merger rates were at their peak. Galaxies were closer together. Collisions were more frequent. When galaxies merge, vast quantities of gas are disrupted and driven toward the galactic centers. This fuels star formation, enormous bursts of star formation called starbursts, and simultaneously fuels the central black holes, triggering quasar activity. The most massive black holes we know of, ton 618, and the handful of other ultramassive quasars formed during this epoch. They grew fast, they grew massive, and then, as the universe expanded and galaxies spread apart and gas was consumed or expelled, they went dormant. The fuel supply dwindled. The quasar era ended. Today, 13.8 billion years after the Big Bang, the universe is a quieter place. The quasar epoch is over. Most supermassive black holes are starving. The cosmic star formation rate has dropped to a tiny fraction of its peak. The great era of construction is largely finished. When we look out at distant quasars today, we are looking back in time. The quasars we see are not current events. They are fossils of light from billions of years ago, reaching us now because light travels at a finite speed. TON 618's light left 10.4 billion years ago. We are seeing it as it was during the quasar epoch, at its peak of activity. The black hole that powered TON 618 during that epoch still exists today. It did not evaporate. It did not collapse. It grew slightly, perhaps accreting stray gas and occasional infalling stars over the subsequent billions of years. But it is no longer actively feeding. It is dark. It is dormant. And it is enormous. 66 billion solar masses sitting silently at the center of what is now an evolved quiescent galaxy. There is a class of galaxies called brightest cluster galaxies, or BCGs. These are the largest galaxies in the universe, sitting at the centers of galaxy clusters. They are thought to have grown by the repeated merger and cannibalization of smaller galaxies over billions of years. The most massive of these galaxies contain ultramassive black holes, the dormant descendants of ancient quasars like TON 618. The black holes at the centers of BCGs are the largest objects of any kind in the universe. They contain more mass than most galaxies. They are not stars. They are not galaxies. They are not clouds of gas. They are singularities, or whatever replaces singularities in the correct theory of quantum gravity, surrounded by event horizons larger than solar systems, sitting at the centers of galaxies, invisible and inert, waiting. If the universe continues expanding and the proton is eventually unstable to decay, as some extensions of the standard model of particle physics predict, then, in roughly 10 to the 36 years, ordinary matter will have dissolved. The stars will have long since burned out. Planetary systems will have been disrupted. Galaxies will have dispersed into thin hazes of dark objects, and the black holes will remain for much longer. Stephen Hawking showed in 1974 that black holes are not truly permanent. Through a quantum mechanical process called Hawking radiation, black holes slowly emit energy and gradually lose mass. For a stellar mass black hole, the Hawking radiation temperature is incomprehensibly cold, far colder than the current temperature of the cosmic microwave background. Currently, stellar black holes are absorbing CMB photons faster than they emit Hawking radiation. So they are growing, not shrinking. But as the universe continues expanding and cooling, eventually the CMB temperature will drop below the Hawking temperature of even stellar black holes. At that point, they will begin to evaporate. For TON 618's 66 billion solar mass black hole, the Hawking temperature is approximately 10 to the minus 30 Kelvin, incomprehensibly cold. The evaporation timescale is approximately 10 to the 99 years. That is a 1 followed by 99 zeros. For reference, the current age of the universe is approximately 1.38 times 10 to the 10 years. Ton 618's black hole will exist, essentially unchanged, for a duration approximately 10 to the 89 times longer than the current age of the universe. By any meaningful measure, Ton 618's black hole is permanent. It will outlast everything, every star, every planet, every atom of ordinary matter. In the final epochs of cosmic history, when the universe is dark and nearly empty, when even the largest stellar black holes have evaporated, Ton 618's remnant will still be there. Still enormous, still waiting, radiating its nearly imperceptible Hawking radiation into an empty cosmos. The last things left in the universe will be the descendants of objects like Ton 618. The universe ends with black holes, and then, eventually, even those go. Ton 618 holds the record for the most massive confirmed black hole, but it does not stand entirely alone at the extremes. There are other contenders, other objects that push against the same boundaries, and understanding where Ton 618 fits among them illuminates just how special it is. Let's build the list from the top down. Ton 618, 66 billion solar masses. Quasar at Z equals 2.219, 10.4 billion light-years away. This is the confirmed champion. No single measurement of any other black hole has returned a higher confirmed mass. Home 15A star. This is the black hole at the center of galaxy Home 15A, the brightest galaxy in a galaxy cluster called Abell 85. For a time, some measurements suggested Home 15A star might rival or exceed Ton 618. The most recent detailed modeling gives a mass of approximately 40 billion solar masses, with significant uncertainty. Home 15A is at a distance of about 700 million light-years, far closer than Ton 618, which is why we can study its host galaxy in detail. The black hole is notable not just for its mass, but for the peculiar structure of the galaxy around it. The central region shows an extremely low density of stars, a core depleted of stellar material. This core scouring is thought to result from a historic merger between two massive black holes that, during their orbital decay and final merger, ejected stars from the galactic center through gravitational slingshot effects. The empty core is a fossil of the black hole merger. NGC 1600, a relatively isolated elliptical galaxy, more distant from any galaxy cluster than typical massive ellipticals. Its black hole mass is estimated at approximately 17 billion solar masses. What is remarkable about NGC 1600 is that its mass is unexpectedly high for an isolated galaxy. Typically, the most massive black holes are found at the centers of the most massive galaxies, in the densest environments at the hearts of galaxy clusters. NGC 1600 breaks this pattern, suggesting that ultramassive black holes can form in environments less extreme than previously assumed. IC 1101, the largest galaxy known by volume, a supergiant elliptical at the center of the Abell 2029 galaxy cluster. Its black hole mass is less precisely determined, but is estimated at tens of billions of solar masses. IC 1101 itself is extraordinary. It is roughly 50 times the size of the Milky Way, containing an estimated 100 trillion stars. Its central black hole, though not precisely measured, is almost certainly among the most massive in the observable universe. M87 star, the first black hole ever imaged directly, at 6.5 billion solar masses. now one of the best characterized supermassive black holes in existence. The Event Horizon Telescope image of 2019 showed the glowing accretion ring and the dark shadow of the event horizon with a resolution sufficient to distinguish features of the black hole. Environment. Follow-up images have shown the ring structure varying over time, consistent with material orbiting at relativistic velocities. M87 star has become the reference object against which other measurements are calibrated. And then Sagittarius A star, our own galaxy's central black hole, at 4 million solar masses, imaged by the Event Horizon Telescope in 2022. Small by the standards of this list, but our closest supermassive black hole at 26,000 light-years. It is currently nearly dormant, but has had active episodes in its past. Evidence in the surrounding region, hot gas clouds, and what appear to be ancient jet structures suggests Sagittarius A star was more active as recently as a few million years ago. On the timescale of the universe, it shut off very recently. What these objects share: TON 618, Home 15A star, NGC 1600, IC 1101's central black hole, is that they all formed during the quasar epoch and grew to extreme masses, primarily through rapid accretion in the universe's first few billion years. They are relics of a violent era, frozen monuments to the most energetic period in cosmic history. The distribution of black hole masses follows what astronomers call the M-sigma relation. The mass of a supermassive black hole correlates remarkably tightly with the velocity dispersion of stars in the central bulge of its host galaxy. Velocity dispersion is a measure of how fast the stars are moving in random directions. It is a proxy for the total mass of the bulge. The tighter the correlation, the more directly the black hole's growth is connected to the galaxy's growth. This correlation is one of the deepest puzzles in galaxy evolution. Why should the black hole, tiny by galactic standards, occupying the central few light-years of a galaxy spanning thousands of light-years, be so precisely calibrated to the galaxy as a whole? The answer is feedback. The energy output of the quasar radiation, winds, jets, regulates the growth of both the black hole and the surrounding stellar population. When the black hole grows, it produces more radiation and drives stronger winds, which heat and expel gas, suppressing both star formation and further black hole accretion. When it is starved, it quiets, gas cools, falls in, and the cycle restarts. This self-regulation is why the black hole mass tracks the galaxy mass so precisely. They are co-evolving, each limiting the growth of the other, settling into a final state determined by the balance between gravitational infall and energetic feedback. TON 618 represents the maximum end of this distribution, the most extreme case. The most massive black hole that the co-evolution between black hole and galaxy, operating during the universe's most productive epoch, produced. At 66 billion solar masses, it is at or near the theoretical ceiling for supermassive black hole mass under the self-regulation model. It may be the most massive black hole that will ever exist in the observable universe. The quasar epoch that produced it is over. The universe today cannot replicate the conditions that grew TON 618. The gas is too sparse, the merger rate too low, the available fuel too depleted. The record TON 618 set 10 billion years ago may stand for the lifetime of the universe. There is a philosophical dimension to TON 618 that goes beyond the numbers. The object itself is extreme. But the fact that it exists, that we can measure it, that we can know it, tells us something important about the universe we live in. The first thing it tells us is that physics is universal. The same laws of gravity, the same nuclear physics, and thermodynamics and quantum mechanics that governs the fall of a dropped apple and the orbit of the moon and the nuclear reactions in the sun. Those same laws apply, without modification, at the scale of ton 618. A 66 billion solar mass black hole is extreme, but it follows the same Kerr metric, the same Schwarzschild solution, the same Penrose-Hawking theorems as a 5 solar mass stellar remnant. The laws of physics don't have different versions for different scales. What works for the small works for the unimaginably large. This is not obvious. It did not have to be this way. It could have been that physics at the scale of 10 to the 40 kilograms follows different rules. There is no logical requirement that the equations hold across 40 orders of magnitude in mass. But they do. Every observation we have made, including of objects as extreme as ton 618, is consistent with the same physical laws we derived from experiments on Earth. The universe is, at the deepest level, consistent, mathematically unified across all scales. That is extraordinary. The second thing ton 618 tells us is about time. It is 10.4 billion light-years away. The light we observe left ton 618 10.4 billion years ago. We are not seeing ton 618 as it is today. We are seeing it as it was when the universe was young, when it was only 3.4 billion years old, just a quarter of its current age. Looking at ton 618 is literally looking back in time. Not metaphorically, literally. The photons arriving at our telescopes from ton 618 have been traveling since before the Earth existed. Every observation of a distant object is an observation of the past. The farther away, the further back in time. The universe is a time machine built into space itself, and the speed of light is the speed at which the past reveals itself to observers in the present. When we look at ton 618, we see the violent youth of the universe. When we look at nearby galaxies, we see its middle age. When we look at each other across a room, we see an imperceptibly small fraction of a second into the past. The same physics, the same light speed delay, the same looking back in time, just at scales too small to notice in everyday life. The third thing ton 618 tells us is about our own position. We are in a galaxy with a 4 million solar mass central black hole. Sagittarius A star is currently dormant, the Milky Way's quasar epoch, because every large galaxy had one ended billions of years ago. We live in the quiet aftermath of a violent past. The scars of that past are written in the structure of our galaxy, in the ancient stellar populations, in the shape of the galactic bulge, in the properties of Sagittarius A star itself. The Milky Way's quasar era produced a black hole of 4 million solar masses. Ton 618's host galaxy produced one of 66 billion. This difference reflects the different histories, the different environments, the different rates of merger and accretion that characterized those two galaxies during their most active periods. We live in a relatively modest galaxy. Ton 618's host galaxy was among the most extreme in the observable universe. We are fortunate to live where we do. A quasar at our galactic center, at full power, would be extraordinarily bright in the night sky, visible in daylight, and would irradiate Earth with X-rays and gamma rays at levels far above what life tolerates. the quietness of our current galaxy is not guaranteed. It is the result of our galaxy having passed through its quasar phase billions of years ago and exhausted the conditions required to sustain it. Sagittarius A star, dormant and dark, sits 26,000 light-years away. It occasionally flares briefly when gas or a disrupted star falls in. These flares are orders of magnitude less luminous than any historical quasar activity, but they are reminders that the mechanism is still there. The engine is cold, the fuel is gone, but the machine is intact. The fourth thing Ton 618 tells us is about limits, physical limits, astrophysical limits, cosmological limits. Ton 618 is at the upper end of what the universe has produced in terms of black hole mass. It may represent a hard ceiling, the maximum black hole mass achievable given the conditions of the quasar epoch and the self-regulation feedback between black holes and galaxies. The universe built things as extreme as they could be built, given the laws of physics and the conditions of the early cosmos. And then it moved on. We live in the aftermath of the universe's most productive era, surrounded by the relics, galaxies, quasar remnants, galaxy clusters of a time when everything was being built. The stars are still burning. New ones still form, though at a fraction of the rate during cosmic noon. The universe is still productive, but its most spectacular constructions are behind it. Ton 618 is a monument to what the universe was capable of. To truly understand Ton 618, not just the numbers, but what those numbers physically mean, you need to understand something about gravity that Isaac Newton never told you. Not because Newton was wrong, exactly, but because Newton's version of gravity is incomplete. And at the scale of a 66 billion solar mass black hole, the incompleteness matters enormously. Newton described gravity as a force, a pull between masses, acting at a distance, proportional to the product of the masses and inversely proportional to the square of the distance between them. Newton's law of gravitation is extraordinarily accurate for describing planetary orbits, tidal forces, the trajectories of spacecraft, and essentially everything humans encounter in daily life. It got us to the moon. It guided Voyager to Neptune. For any practical human purpose, Newtonian gravity is sufficient. But Newton's gravity has a problem. It requires a force to act instantaneously across any distance. If the sun was suddenly removed, Newton's gravity says the Earth would immediately feel the change, zero delay. This violates the principle that no influence can travel faster than light, a principle Einstein established with special relativity in 1905. Einstein's solution, completed in 1915 as the general theory of relativity, was radical. He proposed that gravity is not a force at all. It is the curvature of space-time itself. Space-time is the four-dimensional fabric of reality, 3 dimensions of space plus 1 of time, woven together into a single continuum. Mass and energy warp this fabric. A massive object like the sun creates a depression in the space-time around it. Other objects, moving through that warped space-time, follow paths that curve toward the mass, not because they are being pulled by a force, but because the geometry of space tells them that the shortest, most natural path through space-time is curved. The analogy often used is a heavy ball placed on a stretched rubber sheet. The ball creates a depression, and a smaller ball rolling nearby will follow a curved path toward it. The analogy is imperfect rubber sheets are 2-dimensional, and gravity is 3-dimensional space-time curvature. But the principle is right. Mass curves the geometry. Motion through that geometry follows the curves. For ordinary masses like planets and stars, the curvature is gentle. Space-time is slightly warped near Earth, which is why you weigh what you weigh. It is more strongly warped near the Sun, which is why the planets orbit the way they do. Mercury, closest to the Sun, and therefore in the most curved part of the solar space-time, shows a small discrepancy from Newton's prediction, a precession of its orbit of 43 arc-seconds per century that Newton couldn't explain. But general relativity predicts exactly. This was one of Einstein's early confirmations. As mass becomes more concentrated, the curvature increases. The surface of a neutron star, a collapsed stellar core containing perhaps 2 solar masses in a sphere only 10 kilometers across, has space-time curvature far more severe than any ordinary stellar surface. Escape velocity from a neutron star surface is roughly half the speed of light. Clocks on the surface run significantly slower than clocks far away. Space-time is visibly distorted. Keep compressing. Keep increasing the density. At some point, the escape velocity reaches the speed of light. The curvature of space-time becomes so extreme that the geometry simply does not contain an outward direction. Every path through the space-time geometry leads inward. That is the event horizon. That is where the black hole begins. Inside the event horizon of ton 618, the curvature of space-time is so extreme that something deeply counterintuitive happens to the nature of time itself. The time dimension and one of the space dimensions swap roles. Outside the event horizon, you can choose to move or not move in the spatial direction toward the black hole. You can move toward it or away from it. Time flows forward whether you want it to or not. Inside the event horizon, the direction toward the center of the black hole becomes the time direction. You cannot choose not to move toward the singularity any more than you can choose not to move forward in time. The spatial direction pointing toward the center has the character of a temporal direction. Inevitable, unidirectional, impossible to resist. This is what makes a black hole at the most fundamental level. Not a strong force pulling you in, a geometry that makes inward toward the singularity the future direction. You do not fall into a black hole. You fall toward your own future, which happens to be located at the singularity. This is general relativity. This is what mass does to space-time at extreme densities. And for 66 billion solar masses, the scale of this effect is such that the region where all futures lead inward has a radius of 196 billion kilometers, larger than the distance from Earth to Pluto. The universe has created a region of space-time the size of a solar system, where the concept of getting farther away from something has been erased from the laws of physics. General relativity also predicts gravitational time dilation. Clocks in stronger gravitational fields run slower. A clock near the event horizon of ton 618 would run slower, from the perspective of a distant observer, by a factor that approaches infinity at the event horizon itself. 1 second of proper time near the event horizon corresponds to years or centuries of time for a distant observer. This is not an illusion or a metaphor. Time itself runs differently in different gravitational environments. The GPS satellites orbiting Earth must have their clocks corrected for this effect, or GPS navigation would develop errors of kilometers within hours. General relativity is not an abstract theory. It is an engineering requirement for technology we use every day. At ton 618 scale, the time dilation effects are proportionally more extreme. The space-time curvature is more severe. The region affected is larger. The physics is the same equations, the same constants, the same principles, just applied to a mass so large that the consequences are visible on scales a human cannot easily picture. There is one more thing general relativity predicts about black holes that is relevant to ton 618: gravitational waves. When two massive objects orbit each other, they generate ripples in space-time gravitational waves. These waves carry energy away from the orbiting pair, causing the orbit to gradually shrink. Eventually, the two objects spiral together and merge. The final merger emits a burst of gravitational wave energy that, for massive enough objects, can be detected by instruments like LIGO and Virgo on Earth. In 2015, LIGO detected gravitational waves from the merger of two stellar mass black holes, each about 30 solar masses. The event produced gravitational waves detectable across 1 billion light-years. The energy released in the final fraction of a second of that merger briefly exceeded the luminosity of all the stars in the observable universe combined. Now consider the merger of two ton 618 class black holes. If two black holes of 66 billion solar masses were to merge, an event that almost certainly happened in the early universe, as the predecessors of today's ultramassive black holes went through multiple merger events, the gravitational wave emission would be correspondingly enormous. These very low-frequency gravitational waves, produced by the mergers of supermassive black holes, are called nanohertz gravitational waves. They form a background gravitational wave signal that permeates the universe, the gravitational wave echo of billions of black hole mergers throughout cosmic history. This background was recently detected by pulsar timing arrays networks of extremely stable pulsars, whose timing can be used to detect the stretching and squeezing of spacetime from passing gravitational waves. The signal is consistent with the expected background from supermassive black hole mergers across cosmic history. We are, right now, detecting the gravitational wave ripples of the mergers that built ton 618 and its kind. The universe is not silent. It is humming with the gravitational waves of its most violent past events. The merger that may have contributed to ton 618's mass is, in a sense, still audible, encoded in the gravitational wave background that propagates through the fabric of space-time right now, passing through you as you lie here, stretching and squeezing your atoms by an amount far too small to measure, but real. You are, right now, being touched by the gravitational echoes of the universe's most violent collisions. The region near a massive black hole is not just extreme in the sense of having strong gravity. It is extreme in the sense that every physical quantity of interest, temperature, pressure, density, radiation intensity, magnetic field strength, velocity of matter is at or near the absolute physical limits permitted by the laws of physics. Let's start from far out and work in. Well outside the event horizon of an active quasar like ton 618, the first thing you would encounter is the broadline region. This is a zone, roughly a light year or two from the center, populated by clouds of gas moving at velocities of thousands of kilometers per second. The gas is illuminated by the accretion disk's intense radiation. It absorbs ultraviolet photons from the disk and re-emits them as visible light, primarily in specific emission lines: hydrogen's Balmer series, oxygen's forbidden lines, carbon and magnesium emission lines. The broad, smeared shape of these lines in the spectrum of a quasar tells us both the composition and the velocity of the gas. The broad line region of ton 618 is where reverberation mapping was applied, measuring the delay in the response of these emission line clouds to fluctuations in the central engine. determining the light travel distance, and thereby the orbital radius. The size of the broad-line region scales with luminosity. For a quasar as luminous as Ton 618, the broad-line region may extend several light-years from the center. Closer in, you reach the accretion disk. The outer regions of the disk are relatively cool millions of degrees and glow primarily in ultraviolet. Moving inward, temperatures rise. At the innermost regions, just outside the innermost stable circular orbit, temperatures reach tens of millions of degrees, and the dominant emission is in X-rays. The density of the disk also varies dramatically with radius. The outer disk is relatively diffuse. The inner disk is compressed by the infalling material, and while still far less dense than a stellar interior, the conditions become extreme. The gas is fully ionized, no neutral atoms exist. Every proton and electron is separated by the thermal energy of millions of degrees. It is a pure plasma, dominated by radiation pressure at the innermost radii. The magnetic field threading the accretion disk is crucial. The disk is not a uniform structure. It is turbulent, threaded by magnetic field lines that are tangled and reconnecting constantly. This magnetic turbulence, described by the magnetorotational instability, a process discovered theoretically by Balbus and Hawley in 1991, is the primary mechanism by which angular momentum is transported outward, through the disk, allowing material to spiral inward toward the black hole. Without magnetic turbulence, the accretion disk would be stable and material would not fall in. The magnetorotational instability is what keeps the quasar fed. At the innermost stable circular orbit, the inner edge of the accretion disk, the situation is extreme. For a non-rotating black hole, this orbit is at 3 times the Schwarzschild radius. For a maximally rotating black hole, it can be as close as the event horizon itself. At these innermost orbits, material is moving at a substantial fraction of the speed of light. The orbit around a rapidly spinning black hole at the innermost stable orbit can have a velocity of 0.5 c or more, 150,000 kilometers per second or more. At these velocities, relativistic effects are not corrections. They dominate. Time runs slower by significant factors. The light coming from the approaching side of the disk is blue-shifted and amplified. The light from the receding side is red-shifted and dimmed. The entire disk is relativistically distorted. If you could photograph the accretion disk of Ton 618, its image would be distorted by both the black hole's gravity and the relativistic motion of the disk material. The inner regions would appear bent and smeared, with the near side apparently brighter than the far side, due to relativistic beaming. This is exactly what was seen in the Event Horizon Telescope image of M87 star in 2019. The bright crescent structure in the image, brighter on one side than the other, is the relativistic Doppler brightening of the approaching side of the accretion disk. The darker region in the center, slightly larger than the event horizon itself, is the photon ring, and shadow the region where light is strongly deflected by the black hole's gravity. Ton 618, at 10.4 billion light-years, is far too distant to be imaged at this resolution with any foreseeable telescope. But the physics is identical. The same relativistic effects, the same photon ring, the same asymmetric brightness exist around 10.618. We simply cannot resolve them from Earth with current technology. Now consider what it means to be an astronomer near Turn 618. Not inside the event horizon. Just in the neighborhood, say, within a light-year of the central black hole. The radiation environment would be instantly lethal to any biological organism and destructive to most known materials. The X-ray and ultraviolet flux from the accretion disk at a distance of 1 light-year from ton 618 would be approximately 10 to the 18 times the X-ray flux from the Sun. At Earth's distance, nothing biological could survive. Nothing fragile could maintain structural integrity for long. The jets, if you were unlucky enough to be in their path, would be worse. The material in the jet is moving at 99% or more of the speed of light. The energy flux from the jet's relativistically beamed radiation would be incomprehensible to any engineering standard we possess. A spacecraft in the path of the jet would be obliterated. Outside the jets, at some distance from the accretion disk, the environment becomes merely extreme rather than instantly destructive. The gas of the broad emission line region, moving at thousands of kilometers per second, irradiated from below by the accretion disk, is still a plasma in which no chemistry and no biology as we know it is possible. But it is material that a physicist can characterize. It has a temperature. It has a density. It has a composition that spectroscopy can measure. The host galaxy surrounding the central engine, at distances of thousands of light-years from the center, is where normal astrophysics reasserts itself. Stars form. Stars burn. Some fraction of the stars have planets. The quasar's radiation field is intense throughout the galaxy, suppressing star formation in some regions and irradiating planetary atmospheres in others. Any planetary system within the inner regions of the host galaxy would be bathed in X-ray and ultraviolet radiation levels hostile to complex chemistry. The habitable zones of any stars close to the center would be strongly irradiated. But the outer regions of the galaxy, tens of thousands of light-years from the center, might be relatively shielded. Stars and their planets at these distances, behind the bulk of the galaxy's gas and dust, might experience radiation levels not dramatically different from what Earth experiences from the Sun. Life, under some conditions, might be possible in the outer regions of a quasar's host galaxy. This is speculative. We have no data on planets in quasar host galaxies, and the formation conditions for planets during the peak quasar epoch are very different from the relatively quiet environment of the modern Milky Way. But it is not physically ruled out. The universe is not uniformly hostile to complexity. Even in the neighborhoods of the most extreme objects, most of the space, most of the volume of the galaxy, most of the stars in it is at distances where the central engine's effects, while present, are not necessarily incompatible with chemistry or even biology. The extremes of the universe and the conditions for life occupy the same cosmic structures, just different scales within them. The concept of a black hole did not appear fully formed. It emerged over 2.5 centuries, through the work of dozens of physicists and astronomers, through theoretical predictions, through observational evidence, through skepticism, and through the gradual acceptance that the universe is stranger than anyone initially imagined. The first person to propose something like a black hole was John Michell, an English clergyman and natural philosopher, who in 1783 wrote a paper to the Royal Society of London. Michell applied Newton's corpuscular theory of light, the idea that light is made of particles, and asked, if light is made of particles, could gravity slow it down? Could an object be massive enough that light particles could not escape its gravity? He calculated that a star with the same density as the Sun, but 500 times larger in radius, would have an escape velocity equal to the speed of light. Light emitted from its surface could not escape. Such an object, Michell noted, would be invisible. He called it a dark star. Pierre-Simon Laplace made similar calculations in 1796 in his Exposition du Système du Monde. These early predictions were based on Newtonian mechanics. They were qualitatively right, the idea of an object from which light cannot escape, but built on an incorrect physical framework. Newton's corpuscular theory of light was eventually replaced by the wave theory, and the Newtonian escape velocity calculation doesn't apply directly to modern physics. But the intuition was correct. General relativity gave the concept its first rigorous foundation. Einstein published his field equations of general relativity in November 1915. Within weeks, Karl Schwarzschild, a German physicist serving in the Russian front during the First World War, solved Einstein's equations for the simplest case: a perfectly spherical, non-rotating, uncharged mass. He sent Einstein his solution from the trenches. Einstein presented it to the Prussian Academy in January 1916. Schwarzschild died a few months later of illness contracted at the front. Schwarzschild's solution contained a singularity, a point where the mathematics broke down and the metric coefficients became infinite. This occurred at what we now call the Schwarzschild radius. At the time, most physicists, including Einstein, assumed this was a mathematical artifact, a sign that the physical conditions were extreme, but not that such an object could actually exist. Surely, they thought, matter could not be compressed to such densities in nature. For decades, the physics of the Schwarzschild radius was not taken seriously as a description of real objects. The term black hole wasn't even coined until 1967, when physicist John Wheeler used it in a lecture, and it caught on. Before that, the mathematical objects were called frozen stars, Schwarzschild singularities, or collapsed stars. The shift began in the 1930s. Subramanian Chandrasekhar, an Indian physicist who would later win the Nobel Prize, calculated in 1930 that white dwarf stars, the compact remnants of lower mass stars, had a maximum mass. Above about 1.4 solar masses, no white dwarf could support itself against gravity. Something else would happen. Chandrasekhar's result was dismissed by Arthur Eddington, the most influential astrophysicist of the era. Eddington insisted that nature would find some way to prevent the catastrophic collapse. He was wrong. In 1939, Robert Oppenheimer and Hartland Snyder published a paper solving the equations of gravitational collapse for a massive star. They showed mathematically that a sufficiently massive star, when it collapsed, would pass through the Schwarzschild radius and create what we would now recognize as a black hole. The collapse, from the perspective of the infalling matter, happens quickly. From the perspective of an outside observer, the collapse appears to slow and freeze as the light becomes infinitely red-shifted. Oppenheimer moved on to other work. The war intervened. The Manhattan Project. The world was focused elsewhere. The paper on gravitational collapse was largely ignored for nearly 2 decades. In the late 1950s and 1960s, a new generation of physicists returned to the question. Roger Penrose proved that the singularity inside a collapsing star was not an artifact of the simplifying assumptions made in Oppenheimer's calculation. It was a genuine, inevitable feature of any sufficiently massive gravitational collapse. This is the Penrose singularity theorem, and Penrose received the Nobel Prize for it in 2020. Stephen Hawking extended Penrose's work, proving singularity theorems for cosmological settings, and developing the detailed thermodynamics of black holes, including the famous result that black holes have a temperature and emit thermal radiation, Hawking radiation through quantum mechanical processes near the event horizon. Meanwhile, observers were finding real evidence. The discovery of quasars in the 1960s, those incomprehensibly luminous distant objects that had to be powered by something more energetic than nuclear fusion, forced the theoretical and observational communities to take supermassive black holes seriously. The only mechanism capable of explaining quasar luminosities was accretion onto a supermassive black hole. Through the 1970s, 1980s, and 1990s, evidence accumulated. X-ray binary systems where a stellar mass black hole was accreting material from a companion star provided the first strong observational evidence for stellar mass black holes. Detailed studies of galaxy centers revealed evidence for supermassive compact objects in many nearby galaxies. In the 1990s, long-term observations of stars orbiting the center of the Milky Way, led by teams under Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute, tracked individual stars on orbits around them. Invisible central mass. The orbits were extremely precise. The central mass was confined to a region only a few times the size of the event horizon of a typical supermassive black hole. By the 2000s, the case for Sagittarius A star being a real supermassive black hole was effectively airtight. Ghez and Genzel shared the Nobel Prize for this work in 2020. And in 2019, the Event Horizon Telescope, a global network of radio telescopes operating as a single Earth-sized interferometer, produced the first image of a black hole's event horizon shadow. The target was M87 star, 6.5 billion solar masses, at the center of galaxy Messier 87. The image showed a bright ring of emission surrounding a dark central region, the shadow of the event horizon, where light is captured by the black hole. In 2022, the Event Horizon Telescope produced a similar image of Sagittarius A star. From John Mitchell's paper in 1783 to the Event Horizon Telescope image in 2019. 2.5 centuries from the first theoretical inklings to the direct visual confirmation that these objects exist. And they are as extreme as the equations said they would be. The universe, it turns out, does not flinch. It builds the most extreme things the laws of physics allow. Stars collapse into neutron stars and black holes exactly as predicted. Supermassive black holes sit at the centers of galaxies exactly as predicted. The event horizon exists exactly as predicted. TON 618 is the most extreme confirmed example of all of it. The largest object in the catalogue of the universe's extremes. And it was found by starting with entry 618 in a survey of blue objects in the Mexican sky. Science is patient. The universe was always there. We just had to look. There is a version of the TON 618 story that stops at the numbers. 66 billion solar masses. 10.4 billion light-years. Event horizon larger than a solar system. Luminosity of 140 trillion suns. Numbers stacked on numbers, until the mind surrenders and files it away under very large and moves on. That version misses what is actually interesting. What is interesting is the relationship between you and TON 618. Not the numbers individually, but what they mean in connection to the fact that you exist, and you are aware of them. Let's trace it. The universe is 13.8 billion years old. The first stars formed perhaps 100 to 200 million years after the Big Bang. Those stars were population 3 stars, pure hydrogen and helium, no heavy elements. They were enormous and brief. They burned through their fuel in a few million years and exploded as hypernovae, scattering the first heavy elements, carbon, oxygen, nitrogen, silicon, iron into the interstellar medium. The second generation of stars, population 2 stars, formed from this enriched gas. They contained small amounts of heavy elements mixed into a mostly hydrogen composition. Some population 2 stars still exist in our galaxy today, in the ancient globular clusters and the galactic halo. They are some of the oldest objects in the Milky Way. Their heavy element content is measurable in their spectra. It is low, a fraction of a percent of the Sun's heavy element content. But it is there, the first enrichment of the universe. As the universe evolved and more generations of stars lived and died, the heavy element content of the interstellar medium increased. Each stellar generation added new carbon, new oxygen, new iron, new silicon and calcium and phosphorus, new nitrogen. The full periodic table of elements that life requires was built up gradually over billions of years of stellar nuclear synthesis. The Sun formed 4.6 billion years ago, from a cloud of gas and dust that had already been through several generations of stellar processing. The Sun's composition reflects billions of years of galactic chemical evolution. It is roughly 1.4% heavy elements by mass. The previous generation of stars had lived and died and contributed their elemental products to the gas cloud that became the solar system. The Earth formed from the material that didn't fall into the Sun during the solar system's formation. Heavy elements concentrated in the inner solar system rock-forming silicates, iron, nickel, and built up into the terrestrial planets. Earth is, in terms of its rock and metal, almost entirely made of elements forged in stellar interiors and scattered by stellar explosions before the Sun existed. Life on Earth is built from heavy elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. These 6 elements make up the bulk of every living organism. Carbon and oxygen and nitrogen were all forged in stellar interiors and scattered by supernovae before the solar system existed. You are made of stellar material. Every atom of carbon in your cells was forged in the triple alpha process in the core of a red giant star billions of years ago. Every atom of oxygen in the water in your body was made in helium burning in a massive star. Every atom of iron in your blood was synthesized in the core of a star that ended as a supernova, scattering its contents across the interstellar medium to eventually find their way into the gas cloud that became the solar system, then into the Earth. Then, after billions of years of geological and biological processing, into you. This is not a metaphor. It is nuclear astrophysics. The elements in your body have an astronomical provenance. You can trace them back to specific types of stellar nucleosynthesis processes. You are third-generation stardust, at minimum. Now, where does Ton 618 fit into this? Ton 618's black hole formed, grew, and reached its peak activity approximately 10 billion years ago. At that time, our solar system did not exist. The atoms of your body had not yet been assembled. The star that would eventually produce the carbon that would eventually become part of you had not yet been born. The universe was younger, denser, more active. While Ton 618 was blazing at 140 trillion solar luminosities, the galaxy that would become the Milky Way was still in the early stages of assembly. The halo stars of our galaxy, the oldest stars, the population 2 stars in the globular clusters, were being formed during this epoch, in the same general era when Ton 618 was active. While Ton 618's accretion disk poured out X-rays and ultraviolet radiation, and drove quasar winds at 10% the speed of light. The stars of the Milky Way's thick disk were forming from gas enriched by the first stellar generations. The universe was doing many things simultaneously. In some corner of the cosmos, 10 billion years ago, a black hole of 66 billion solar masses was accreting at near Eddington rates and outshining entire galaxy clusters. In another corner, far away in the causally disconnected region we now call the local group, the gas and dark matter that would eventually become our galaxy were assembling more quietly. Time passed. The quasar epoch ended. Ton 618 went dark. The universe expanded, cooled, became the quieter place we inhabit today. 4.6 billion years ago, a small perturbation in a gas cloud in the outer Milky Way triggered gravitational collapse. A star ignited. The leftover disk of gas and dust cooled and aggregated into planets. One of those planets, the third from the new star, had liquid water, had a reducing atmosphere that evolved over billions of years to an oxygen-rich one, had chemistry that spontaneously organized into self-replicating molecules, had natural selection acting on those molecules for 4 billion years, and eventually had you. You are the universe's way of knowing itself, not a metaphor, a literal description of what has happened. The universe existed for 13.8 billion years. In the last few 100,000 of those years, a species arose on a small planet that was capable of asking questions about the universe's nature and arriving at answers. Those answers include the existence and mass of Ton 618. The same universe that produced Ton 618's 66 billion solar mass black hole produced the atoms, the planet, the biology, and the intelligence that could measure it. The relationship is not accidental, it is causal. The heavy elements produced by the stellar generations that preceded the Sun, some of those stellar generations happening in galaxies that may have hosted quasars comparable to Ton 618, were prerequisites for the formation of rocky planets. Rocky planets were prerequisites for chemistry. Chemistry was a prerequisite for biology. Biology was a prerequisite for you. You exist because stars exploded. You understand Ton 618 because of 13.8 billion years of cosmic evolution, stellar death, planetary formation, and biological evolution that produced creatures capable of spectroscopy and reverberation mapping and general relativity. The universe has always contained Ton 618. The photons from its accretion disk have been traveling toward us since before the Sun was born. They have been in transit, crossing the cosmic web for 10.4 billion years, waiting to arrive at detectors operated by creatures who could understand what they were seeing. This is what makes the discovery of Ton 618 more than a measurement. It is a moment in the universe's self-knowledge. The universe looking at its own most extreme construction and measuring it. Not from outside the universe, there is no outside. From inside it, with instruments made of atoms forged in stars, operated by intelligences that evolved on a planet orbiting one of those stars, in one of those galaxies. You are not separate from Ton 618. You are part of the same universe, made of the same physical laws, continuous with it through 13.8 billion years of causally connected events, each one following from the last, according to the same mathematics that describes the event horizon. The distance between you and Ton 618 is 10.4 billion light-years. That is a real distance. It is enormous. By any human standard, it is inaccessible. No signal you could send would reach Ton 618 during the lifetime of the universe, given its expansion. No physical journey there is conceivable. The distance is, for all practical purposes, infinite, and yet you know it. You know its mass, its luminosity, the size of its event horizon, its distance and its redshift, and the nature of its accretion disk and the physics of its formation. You know all of this because light photons that left TON 618 before Earth existed carried that information across 10.4 billion light-years and delivered it to human instruments. Knowledge travels at the speed of light. Understanding requires a receiver capable of decoding it. The universe spent 13.8 billion years building such a receiver. You are part of it. Tonight, lying here, you are part of a universe that is aware of its own most extreme object. That awareness exists in you, built from the same physical laws that built TON 618 itself, separated from it by an enormous distance, but connected to it by physics, by light, by the 13.8 billion year chain of causation that runs from the Big Bang through every generation of stars, to the solar nebula, to the Earth, to you. You are, in the most literal sense, how the universe knows what 66 billion solar masses looks like. That is not a small thing. There is one final piece of TON 618 story that we have not yet told. A piece that sits at the boundary between what we know and what we do not yet understand. A problem so deep and so unresolved that it has occupied the finest minds in theoretical physics for 50 years without a complete solution. The black hole information paradox. In classical general relativity, a black hole is simple. When matter falls into a black hole, the details of what fell in are lost. The black hole is entirely described by three quantities: its mass, its electric charge, and its angular momentum, its spin. Everything else about the infalling matter, the composition, the structure, the information about what it was, is gone. A black hole made from a collapsed star and a black hole made from an equal mass of antimatter look identical from outside. The information about what made them is destroyed. This was acceptable in classical physics. Classical physics does not have an absolute conservation law for information. Quantum mechanics does. In quantum mechanics, the evolution of a physical system is described by a wave function. The wave function evolves according to the Schrödinger equation, which is unitary, meaning information is conserved. If you know the wave function at one time, you can determine it at any other time, past or future. Information is never created or destroyed. This is called unitarity, and it is one of the deepest principles in quantum mechanics. In 1974, Stephen Hawking showed that black holes are not truly black. Through quantum mechanical processes near the event horizon, pairs of virtual particles are created from the vacuum. One particle of the pair falls into the black hole. The other escapes as Hawking radiation. The black hole slowly loses mass. If nothing else changes, the black hole evaporates completely over an incomprehensibly long timescale. But here is the problem. Hawking radiation is thermal. It carries no information about the internal state of the black hole. If the black hole evaporates completely into thermal Hawking radiation, the information about everything that ever fell into it, every particle, every quantum state, every bit of structure, is gone. Permanently, irreversibly. This violates quantum mechanics. It violates unitarity. Information cannot be destroyed in a quantum mechanical universe. But if Hawking's calculation is correct, information is destroyed when a black hole evaporates. Either quantum mechanics is wrong, or general relativity is wrong, or Hawking's calculation is incomplete. one of the three. But we don't know which. Hawking himself debated this with John Preskill for decades. The two had a famous bet, settled in 2004, when Hawking conceded that information is probably conserved, that black hole evaporation is somehow unitary, somehow returns the information, encoded in subtle correlations in the Hawking radiation. But the mechanism by which this happens was not known then and is not fully known now. The current leading candidate for a resolution involves something called the Page curve. Don Page showed in 1993 that if black hole evaporation is unitary, the entropy of the Hawking radiation which measures the information should follow a specific curve. It should increase initially, reach a maximum at the Page time, roughly halfway through the evaporation, and then decrease as the information gradually leaks out in increasingly complex correlations among the Hawking photons. Recent work in quantum gravity, particularly using a technique called the island formula, and ideas from holography and the ADS/CFT correspondence, has produced calculations that give the Page curve. This is progress. It suggests that the information is not destroyed, but the precise physical mechanism by which a black hole preserves and emits information remains an open question. For Ton 618, this matters in the following sense. The 66 billion solar masses that make up its black hole contain information, the quantum states of every particle that ever fell in, every atom of gas from the quasar's accretion disk, every photon from the broad emission line region, every electron and proton and photon that has crossed the event horizon since the black hole formed billions of years ago. Quantum mechanics says all of this information is preserved somewhere, somehow. General relativity says it is lost forever. One of them has to give. The resolution of the black hole information paradox will require a theory of quantum gravity, the synthesis of quantum mechanics and general relativity that physicists have been working toward for a century. String theory, loop quantum gravity, and various other approaches all make contact with this problem. None has produced a fully satisfying solution that everyone accepts. Ton 618 is not just the most massive black hole we know. It is also the most massive physical system containing a currently unresolved paradox at the foundations of physics. Somewhere inside the event horizon of Ton 618, if inside means anything in this context, sits the answer to one of the deepest questions in theoretical physics. Not a metaphorical answer, a physical one, encoded in the quantum state of 66 billion solar masses of collapsed matter. We cannot retrieve it. We cannot observe it. We cannot, with any foreseeable technology, probe the interior of Ton 618's event horizon to find the answer. But the answer is there. The universe knows the solution to the information paradox. It has known it since the first quantum state crossed the first event horizon. We just have not figured out how to ask the question in a way the universe can answer. That is the honest state of human knowledge about Ton 618 and about black holes in general. Enormous precision in some things, the mass, the luminosity, the distance, the size of the event horizon. Complete ignorance in others what happens at the singularity, how information is preserved or lost, what quantum gravity looks like at the Planck scale inside the horizon. We are at the beginning, not the end. And lying here tonight, you are part of the species that is asking these questions. That built the instruments. That measured Ton 618 from 10.4 billion light-years away. That found the information paradox. That is working now on solving it. The universe spent 13.8 billion years building something capable of asking what it is made of. Tonight, that something rests. The questions will be there tomorrow. And Ton 618 will still be there, too dark, silent, vast, 10.4 billion light-years away, holding its secrets in the geometry of space-time. Good night.